today we are going to continue from ODEs that we have been looking at, and then so we will develop a useful alternate picture, where we have some qualitative understanding of these systems can be pulled out from an analysis of the so-called phase space picture, right? So oftentimes you don't want to solve the full problem in a brute force way, but you just try to extract as much physics out of it just by looking at the structure of the equations and so on. And so this is where this analysis comes in. And so we will develop this within the so-called linear system approach, where an exact solution is possible. So we will discuss how that happens, and we'll try to fit into this framework, examples which we have already seen. But then what this does is it actually builds a nice platform on which more difficult nonlinear problems can also be analyzed along these lines, where it's not possible usually to find a full analytical solution. So whereas this the insights from this phase space picture will be very useful. Okay, so let's say that you have a system of equations involving two variables. I have taken two variables for simplicity. This can be easily extended to more number of variables, right? So x dot equal to some arbitrary function of x comma y, and y dot equal to some arbitrary function of g. I'm calling it g of x comma y, right? So where the RHS does not depend explicitly on time, right? So we want to develop this phase space picture, so where we just look at, take any point in the xy plane and ask what the point is doing there and where is it headed next. Suppose your system were caught at some time t at some point xy. So this, what is the time doesn't really matter, because you're considering a system where the velocities are determined only by where you are. So you are going to be able to extract a flow of where this system is tending, and then by studying the dynamics of this flow, a lot of very interesting and a lot of insights can be drawn from a qualitative study of these phase portraits, as they are called. And Mathematica has a very useful plotting function, which is we'll use this thing called stream plot. You can play with vector plot and how basically carry out these kinds of studies, right? So what we do is we just look at the trajectory of this particle based on the magnitude and the direction of the flow, right? So let's look at a very simple example first. Suppose I have a system where x dot is equal to y and y dot is equal to minus x, right? So if you can pause the video for a moment and convince yourself that this is a problem that you already solved. What is this problem? Okay, so now I'm going to continue and tell you the answer. So the solution is, of course, first of all, I'll write down the solution, which is just x of t is equal to a times cosine of t plus t naught, and y of t is equal to minus a times sine of t plus t naught. The solution is this because it's really the harmonic oscillator. You can think of x as the position and y as the one-dimensional speed, right? It's the 1D harmonic oscillator. Very simple problem. If you want to see this, you can write it as x double dot is equal to minus x, and then you will see this. And so the way it works is, to find out the trajectory in the xy plane, you want to eliminate this, these constants. You want to eliminate time, basically. So you want to write it as just functions of x and y. So then you have x squared plus y squared equal to a squared, and depending upon the magnitude of a, you're going to get a circular flow, right? All of this is very nicely visualized with the help of stream plot. So the syntax for stream plot is simply, you must provide the flow magnitude and the direction here in terms of this, these two quantities have to be provided inside these flower braces, y comma minus x in our case. So x dot equal to y, y dot equal to minus x, and then you must tell the limits of x that you're interested in, the limits of y that you're interested in. So x goes from minus 1 to 1 and y goes from minus 1 to 1 is what I'm looking at. If I hit shift enter, then there you go. So you see a nice flow diagram. So this is what is called the phase portrait picture of the harmonic oscillator problem. So it tells you that basically there is no loss of energy, right? So we know this, and the simple harmonic oscillator, the system keeps on going around and round, exchanging kinetic energy to potential energy and potential energy to kinetic energy again and again and again repeatedly. right? And depending upon the radius of the circle that you're in is a measure of that amount of energy that is trapped inside this system, right? Very familiar stuff, but from an alternate picture. Now let's look at another example. Suppose I have x dot equal to x and y dot equal to y, right? So then again you can solve this equation and the answer is just x of t equal to a times. They are uncoupled, right? So x dot equal to x and y dot equal to y. So x is going to keep on increasing, y is also going to keep on increasing. And so in fact y equal to b by a times x. So that's the when time has been eliminated, so you get this kind of a curve in the xy plane, which is nicely shown here with the help of the stream plot. So you see that all these trajectories are straight lines which are all running away from the origin. So if you let a particle be anywhere other than at the origin, right? So if you're at the origin, of course it will stay at the origin forever, but slightly away from the origin, depending upon which direction you're headed in, it's going to just keep on running away to infinity along a straight line, right? So that's what the flow directions are. And then finally we look at a third kind of example where you have x dot equal to y and y dot equal to x, right? So here you can solve for it analytically, and so that answer turns out to be, after elimination you get y squared minus x squared is equal to constant. And here the asymptotes of phase space trajectory are the lines plus or minus x. And now you see that qualitatively the flow is actually quite different from the previous case. And so you see that for long times, if you are in one of these trajectories above, you typically start from somewhere close to the line y equal to minus x if you're coming in from, if you're starting at a large negative time, and for large positive time you're going to approach the plus y equal to x region. If you're, doesn't matter whether in which quadrant you start, it's eventually going to go to y equal to x, and for large negative times you would be very close to the y equal to minus x line, right? So this is what is called a saddle point. So there are these, in fact these three are very characteristic plots, which represent the so-called stable node, unstable node. And so this is actually a very special type, when you have circles all around. This is an unusual kind of a fixed point. There is a fixed point sitting at the origin. So I will talk about this in a moment, but just to step ahead a bit. So there is something called a fixed point which is sitting at the origin. Basically, if you are at the origin in any of these differential equations, you will remain at the origin forever. But if you are slightly away from the origin, in one case, the first case, you are at what is called a neutral fixed point. Is basically going to keep on being at the same distance forever. But if you are in the second case, you're going to run away to infinity, and the third case you would run away to infinity if you're along a certain direction, you're going to run away, but in another direction, if you're carefully located along this line y equal to minus x, then you would actually come back to the origin, right? So this is what is called a saddle point. Yeah, and it's supposed to remind you of a saddle, right, which is put on a horse, and you see that along one direction it is a minimum, but along the other direction it's a maximum, right? So that's where this terminology has its origins from. Okay, so we'll make these notions a little more precise as we go along, but this is just a qualitative understanding of. So let's move ahead and look at a few more examples, and then we will go into the general theory. Okay, so linear systems in general, if I have 2 degrees of freedom, x and y are available, so I can think of a general linear system of this kind. X dot equal to ax plus by, and y dot equal to cx plus dy. A, b, c, d are parameters of your system. So there's a compact way to write this in terms of a vector equation. So x vector dot is equal to matrix A times vector x. Now this matrix A is of course a, b, c, d. So we can ask what will be there is clearly a fixed point at the origin always, right? When x equal to 0 and y equal to 0, for sure your system is not going to move, right? Its dynamics is null. It's just going to remain at the origin forever. But we have seen that depending upon this matrix, the precise values inside this matrix A, the nature of the dynamics can be very different around the origin, slightly away from the origin. That's what we're going to work out. So before we do that, let's quickly identify, which equations correspond to a linear equation, right? So any linear equation necessarily has this form, right? Underlying the linear equation or a linear system is the so-called superposition principle. Basically what it tells you is that if you are able to find two solutions, then any linear combination of these two independent solutions is also a solution, right? So this we have seen, and we have surely some intuitive idea of this. So let's quickly go over this question, right? It's like a quiz if you wish. So you can pause the video for a moment and try to answer for yourself which of these four systems is linear and which of them are not, and I will give out the answer now. So the answer is, of course, A is linear, B is linear. They're very, yeah, I mean, in fact, we have already looked at these examples. They're definitely of the form which is described above. C is not linear because y dot is equal to minus sine of x is involved, so it is not linear. And D is also linear, right? It involves x and y, that's okay. And what about E? Is it linear? It is linear, right? So this is a place where a lot of people get confused. Linearity and order of the differential equation are two different things. So linearity has only to do with, what is the power of your x or x dot. So in this case, you can just define x dot equal to y, and then you can recast it in this canonical form, and it's still going to be linear, right? So if you had mx double dot the whole squared, or sine of x double dot, or something more complicated than that, then it would be nonlinear, and then the dynamics is generally much harder to understand. Okay, so let's move on. So if you have a general 2D linear system of this kind, it's possible to go ahead and solve for it, right? So we know, suppose you have this very special case, x dot equal to ax and y dot equal to dy, which is uncoupled differential equation, then obviously the solution is just x equal to e to the at and y equal to e to the dt, right? So we ask whether the general solution can be of this form, right? Can we take some vector and so the general solution must be such that it's just e to the lambda t times some vector. Is there some special direction which will still yield such simple solutions? And so it turns out that when we make this as an ansatz and plug this into our differential equation, these vectors, we actually get a matrix eigenvalue equation. It becomes an eigenvalue problem. So as you can see, if you plug this x equal to e to the lambda t times vector v into your original problem, x dot equal to ax, so x dot is of course just going to give you lambda times e to the lambda t times v, and then if you plug this in, you really have to solve for a times v equal to lambda times v. So v is nothing but the eigenvector and lambda is the eigenvalue. So if you can find lambda and if you can find all the v's and the lambdas corresponding to them, basically you would have solved this problem. Let's go about doing this systematically. So the eigenvalues of the two-dimensional matrix are conveniently expressed in terms of the trace and the determinant of the matrix as. So it's just simple algebra. If you have not already seen this, I urge you to go back and verify this for yourself. So if lambda 1 and lambda 2 are the eigenvalues of your 2 by 2 matrix, you can write this as lambda 1 equal to tau plus square root of tau squared minus 4 delta divided by 2. This is nothing but the root of a differential equation. You can verify this, solve this for yourself and check this. Tau is the trace of the matrix and delta is the determinant of the matrix. Lambda 2 likewise will be just tau minus the square root of the discriminant divided by 2. Now if nu1 and nu2 are, I guess we have called it v1, so that's fine. So nu1 or v1, whatever you want to call this, are respectively the relevant eigenvectors. So in general, lambda 1 is not equal to lambda 2, and this means that the two eigenvectors are linearly independent and therefore they span the space, right? So if you take a course on linear algebra or in some physics math methods type courses, you may go into some details of when a matrix is diagonalizable and when it will give you eigenvectors which are linearly independent and so on. So but let's not go into that discussion here. Suppose lambda 1 is not equal to lambda 2, then these two eigenvectors are linearly independent and therefore they span the space. Then it's possible to basically expand your initial conditions x naught as a linear combination of these eigenvectors, independent eigenvectors v1 and v2. It's possible to find these coefficients c1 and c2, and once you do this, the general solution is immediately written down. So it's just x of t is c1 times e to the lambda 1 t times v1 plus c to the e to the lambda 2 t times v2, right? So this is something that you might have also seen in a first course on quantum mechanics. If you try to solve the Schrodinger equation is a linear differential equation. So if you are able to find, all the eigenvectors, so what do? You take the initial state of your system, expand it as a linear combination of the eigenfunctions of your Hamiltonian, and then you just simply, the time evolution of your full wave function is given by, these phases attached to the eigenvectors, and these coefficients, these crucial coefficients come from the original expansion of your initial state in terms of the eigenfunction, right? So this is something that you have seen. Okay, so now what I want to do is use this to describe a very interesting problem which is given in Strogat's book on nonlinear dynamics and chaos. So this is about Romeo and Juliet and how their relationship can be modeled as a differential equation. So let R of t be the measure of the love that Romeo feels for Juliet at time t, and let J of t be the measure of the love that Juliet feels towards Romeo. Actually, it should be Romeo. So let's change this. So this is Romeo. Now, the greater the magnitude, the greater the intensity of the feeling. And however, the sign of the quantity determines whether so the sign determines whether it's a positive emotion or it's a negative emotion. So there could be also a repulsion, and the repulsion would come from a negative sign. And the magnitude will give you, the intensity of the feeling. It could be positive or negative. So what you do is you model the dynamics of the relationship as a coupled linear system with fixed rate constants that determine the evolution of their amount of feeling for each other, positive or negative. One instance of this story has the following system. So you say R dot is equal to J and J dot equal to minus 2R, right? So it is an interesting coupled system. So Romeo, being a simple man, he feels greater intensity, and the more that J increases, R also is directly proportional to it, and it's increasing in a positive manner. So the more that Juliet comes towards him, the greater is his feeling for her. But Juliet, on the other hand, is a little more complicated. So she feels attracted towards Romeo as long as he keeps himself at a distance. If he throws himself upon her, so she has a tendency to run away, right? So this is Juliet's nature. And so you can ask what happens to this set of differential equations, and where, what is the fate of their relationship based on our analysis of linear systems. Clearly this is a linear system because you have R dot equal to J and J dot equal to minus 2R in our very simple model. You can of course have a real life scenario, might be even more complicated. It does not have to be exactly so J and minus 2R. It could be something more complicated, but let's say we stick to this model because we are familiar with linear systems, and then see what happens in this case. So let's start by making a phase portrait. So we have our familiar stream plot. Now we make a phase portrait, and there you see you have this picture, which is actually something very familiar. And if you think a moment, you'll see that this is not a surprise at all, because this set of differential equation is something that we have already seen. This is nothing but the problem of the simple harmonic oscillator. It's a 1D problem. So there, the dynamics of the relationship is an unending cycle basically, right? So they're caught in some circle, right, which is determined by the total energy of your system, if you wish, or the intensity of their feeling. But you see that in one quadrant, both R and J are positive. So both of them have mutual interest in each other, and both of them, it's positive in nature. But then there are these three quadrants where at least one of them is negative. So one of them is going behind the other, but the other is unhappy, is running away. And then there is a third quadrant where both of them are basically running away from each other. So it's a 1/4 successful relationship, but somehow at least 1/4 of the time there is mutual harmony and love, and it's a cyclical dynamics all the time. So the most general such linear model that you can think of is, of course, R dot equal to AR plus B times J, and J dot equal to CR plus D times J. So where you can play with all these parameters A, B, C, D and see what happens to their relationship. What is the fate of the relationship based on all these parameters is an analysis that we can do. But before we do that, we will go and develop the full general theory of such a system. So I told you that your eigenvalues are something that you can write down in terms of tau and delta, and in fact all the qualitative nature of these dynamics is just contained in these two parameters, tau and delta. So we will see how you can actually make a phase diagram which tells you the nature of the fixed points underlying them. So the nature of the dynamics, if you wish, and still not defined a fixed point, and based on just tau and delta. So that's coming up next. Thank you for now.